Hi, everyone. I'm Vijay from Wave. I'm very excited to be here. Thank you to the organizers for inviting us to this event. Very happy to be sponsoring it. Wave, if you already didn't know, is an AI company. We're based out of London, but we're fast expanding in Mountain View. Our mission primarily is to reimagine autonomous mobility with embodied intelligence. What this really means is we solely focus on building foundational end-to-end driving models for human-like driving intelligence. Here are a few examples of our driving model operating in London under challenging conditions, expressing some very nuanced behavior around pedestrians, and also generalizing zero-shot to other cities in the UK. Now, the interesting thing here is all of this is learned end-to-end from observing millions of data samples of safe London driving. So we focus on these kind of models, and we build the data platform and the machine learning tools to accelerate building of these models and deploying them. We build for generalization. We want to generalize across cities. We want to generalize across vehicle types and sensing suites. Every day we do grocery deliveries across the UK on random routes, continuously expanding our testing perimeter. The vehicle platforms, we operate on 2 vehicle platforms today, and we will expand to 4 AV platforms. So we use the same foundation models, but deployed across platforms. And we also work with more than one sensing modality. So at Wave, we've been a company, we co-founded the company in 2017, and we recognize the importance of science and investing in it. And these are some of the breakthroughs that come out of the investments. In the middle is Gaia 1, our world model, and Lingo, our vision language model, and Learn Simulator. Come talk to us. If all of this is exciting, come talk to us. There are lots of opportunities to work with us in both the locations. Thank you very much.
Thank you. We're here with Monarch, which is part of Ethicon and the Johnson & Johnson MedTech organization since 2019. Our product is the first and only multi-specialty flexible robotic platform that's cleared for use for both bronchoscopy and urology procedures. The platform integrates the latest advancements in endoscope innovation, instrumentation, controls, algorithms, and software, with the goal of enhancing physician capabilities and improving patient outcomes. To date, we've done more than 30,000 bronchoscopy procedures in the US, and last year we also received FDA clearance for our urology product, and we've been running clinical trials targeted at kidney stone management this year. So the goal is to extend the capabilities of the platform with an exciting pipeline of procedural innovation. If you're interested to learn more about the different roles, both full-time, short-term co-ops, and internships within the Robotics Under Solution organization, and also the different teams, algorithms, controls, software, robotics, and systems, please come talk to us at our booth. Thank you.
Hi. So tell you a little bit about NVIDIA. So we are an AI and accelerated computing company for those who haven't heard of NVIDIA. Yeah, I guess it's a little bit of a joke. So we developed the entire stack from the chips all the way up to the application frameworks and everything in between. And we have 2 main platforms, NVIDIA AI and NVIDIA Omniverse. So NVIDIA Omniverse is a platform for creating and connecting virtual worlds. And it's built on OpenUSD format. And USD is a format developed by Pixar. And Isaac Sim is the robotics simulator that we have. Isaac is the robotics platform that NVIDIA builds. And Isaac Sim essentially is a few components, as you can see here, for robot models for reinforcement learning, behavior programming, and so forth, and built on Omniverse. And Isaac Gym is a platform or an extension, for reinforcement learning inside Isaac Sim, which many researchers have been using. And I also wanted to talk or share with you that we have a lab at Stanford who has actually developed Omni-Gibson, which is essentially for accelerating embodying AI research, and it's built entirely on NVIDIA Omniverse. Thank you.
Hi, everyone. Thanks, Sharon. I think that was actually probably a great advertisement for TRI. I'm not sure I'm going to do anything better here, but TRI there's a couple of locations. There's one down here in Los Altos. There's one in Cambridge. We're about 150 researchers across everything from material science, human-centered AI, robotics, and machine learning. To highlight a few projects that are going on, there's everything from mobile manipulation, where we think about challenge tasks, sort of DARPA hard challenge tasks, such as this grocery store task where we go and try to pick items across thousands of different categories and specific items, and see how our capabilities enable these sorts of technologies. This is also transitioning into things like the factory as well, as we sort of move toward some applications within Toyota. There's also, related to what Sharon was saying, a big manipulation effort as well in Boston, and this is to build lots of different low-level behaviors. And we've actually seen a huge step change with some of the generative AI techniques, such as diffusion policy, and being able to train, 60, hundreds of different tasks. And the promise of having large behavior models eventually is something that we're very interested at Toyota, at TRI generally. Beyond this, we actually have a large language model team to enable some of this downstream as well. We also do vision language models and a wide variety of principle-centric sort of computer vision as well in the machine learning team. With that, there are a few of us here from TRI. Please come find us. We'd love to talk to you. Thanks.
Hi, I'm Vincent Kasser, and I'm excited to tell you a little bit about Waymo today. Waymo stands for a new way forward in mobility. We're an autonomous driving technology company with a mission to make it safe and easy for people and goods to move around. Fully autonomous technology holds the promise to improve road safety and offer new mobility options to millions of people. So most of us are probably familiar with the SAE levels of autonomy. Levels 1 to 3 are driver assist, so you do need to be ready to take over the car as needed. At Waymo, we're pursuing level 4 and above. So that means, unlike other technology that is doing driver assistance, Waymo is always the driver from the beginning to the end, and you will never be required to touch the wheel. So we've been working on this for a while. We started in 2009 as the Google self-driving car moonshot. And among many milestones, we were the first to deliver a fully autonomous ride in 2015, and also started the first commercial autonomous ride-hailing service in 2020. So now we're actually scaling to delivering tens of thousands of rides per day in San Francisco and Phoenix. And we're expanding it to other cities as well. So right now, we're serving riders in these two areas. And in Phoenix, anyone can download the app and ride today. In San Francisco, we're serving well over 1,000 riders right now, and we're looking to enroll more from our waitlist. So the Waymo One app makes it easy to get where you're going. Just download the app and hail a Waymo and get to your destination. So if you're interested, I highly encourage you to go to San Francisco, download the app, and try it out. And you can also go to social media, find lots of videos of the experience if you like. And in this industry, there are unique research opportunities for people to work on foundational models, LLMs, vision language models, neural rendering, and a lot of perception, planning, and related tasks. So please stop by our booth if you're interested. Thank you.
All right. Hi, I'm Stefan. I'm the Chief Science Officer of Intrinsic. That's an advertising talk, so it will be short and it will be shallow, which is much better than it long and shallow, obviously. So What is Intrinsic? Okay, Intrinsic is actually a new subsidiary of Alphabet. It means we're a Google company. That means we belong to Google in simple words. And we are interested in robotics. So kind of the bigger picture in which you can read, we want to make robotics easy for everybody. And as an academic, I'm super interested in that since I've spent countless hours behind robots trying to just get the basics going such you can do research, what you want to do. So what's the motivation? Well, robotics is actually a little bit miserable since it's somehow you have to connect actuators and sensors to the real world and to software and try to make it work. And it's a lot of work, it's systems, and it's just not always fun to get this all together. So we try to do this for others that they can do things better. To be honest, I personally want to be better and I want to profit for myself. So important is, of course, these days, all the sensor processing and also control processing becomes increasingly more artificial intelligence and machine learning, and we try to build this into the system from the very beginning. What's happening in the world of robotics? There's a couple of things which make things different. And one thing is obviously generative AI. Well, repeat it all the time and again and again. There's another thing which is increasingly important, and that is that you build platforms which support all these different things. And I think ROS was really one of the main platforms to get this going. Intrinsic tries to do something similar on a larger scale, on a more modern scale. And if you have noticed, the Open Robotics community, Open Robotics Corporation is the official name, is actually part of Intrinsic by now, and we work together and make this work. And then there's, of course, other cool things. Huge amount of compute power, TPUs becoming increasingly popular, and lots of different kind of sensor modalities which you can draw. TPUs are kind of fun in Google. This is like an aquarium. They're called jellyfish and viperfish and pufferfish, and very bizarre, but they compute really fast. Intrinsic is interesting to get into a large spectrum of applications from basically more structured environments to increasingly more unstructured environments. We started a little bit conservative and try to get better. And we also have some fun interfaces. I can play this. Yep. You can see more about this, and this becomes increasingly more useful for research. And that's pretty much it. You can find things on our webpage. We are always interested in collaborations and interns in the futures. And thank you.
Excellent. So thank you very much to the sponsors, of course, for making all of this work. Up next, we are going to the students. I'd like to suggest that we hold our applause until the end, just because they do go through relatively quickly. I'd like to ask the students to sort of move forward and be ready to go, because we have a relatively long queue.
Do you need some? Yeah. I'm not sure if it'll connect, but... Okay, yeah. Okay, sorry. Hopefully. I don't know if it connects to that, though.
Hello, everyone. I'm Zipen from Stanford University, working with Chelsea Finn. I'm going to show some results from our project with collaborators on robot parkour learning. For more detail, please check out our poster and website, and feel free to send an email. Thank you.
One of the key problems for soft, pneumatic, wearable haptic devices is the difficulty of providing consistent haptic feedback due to the variations in body shape and skin stiffness of users. Instead of internal pressure regulation, soft actuators should be controlled based on interaction force. We designed an integrated pneumatic sensor and actuator, which is a soft actuator capable of detecting contact force, contact location, and its overall shape. We do this by casting an array of pneumatic strain gauges on the surface of a soft actuator and estimating its states using a multi-headed neural network. For more information, please visit my poster.
Hi, my name is Morgan Masters, and the clock has started. Deep learning can accelerate field research, but struggles in novel deployments. This is because of a dependence on annotated training data, which is time-consuming and expensive to generate historically. Because of this, a lot of modern research gets stuck in the labeling bottleneck, where data as cost just precludes deep learning as a feasible tool. In response, my team has built a tool called PinView, which is a field robotics system designed to help field research non-experts develop annotated image data sets for emergent research. We've been general in our design so that you could track disease on a farm field, inspect power lines, or census Arctic polar bears. Calibration is the primary challenge, and I'd love to talk about it at my poster.
Hi, everyone. My name is Shuai Wu from Mechanical Engineering, Stanford University. Stroke is one of the leading causes of death in both the United States and worldwide. Well, considering the increasing number of aging people, this requires more experienced neurosurgeons, especially those operations generally rely on navigation of caster in very tortuous environment until you reach the target position. To help with this, we developed a wireless control robot driven by external magnetic field. The robot can carry out multifunctionalities such as the navigation in complex environment under the guidance of X-ray, as well as in situ drug delivery. Come to my poster for more information. Thank you.
Hi everyone, my name is Rihanna Jatosho, and I'm excited to share our work with you at this year's symposium. Control policies for soft robots often rely on quasi-static assumptions or rely on hand-designed motion plans. In our work, we use reinforcement learning to achieve real-time planning and control of agile behaviors for soft robot arms. So we rely on a deep RL training framework, and we leverage key insights with simulation and actuator modeling to overcome sim-to-real challenges. And this allows us to achieve zero-shot sim-to-real transfer. So here's an example of our framework applied to a shelf-reaching task, and if you'd like to learn more, please stop by our poster. Thank you.
Hi everyone, I'm Jimmy. In our project TidyBot, we look at the task of personalized household cleanup. One of the key challenges here is that people have different preferences. For example, I might want shirts to go on the shelf, whereas my friend might want them in the drawer. So how can robots learn your preferences from just a few examples? Our solution is to use summarization with large language models. We first collected person preferences by asking for a few examples of where different items should go. Then we give these examples to a large language model and ask it to summarize. What comes out of the summarization are general rules that work for novel objects. For further details, please come by our poster or visit our project page. Thank you.
Hi everyone, I'm Shivani. I work at Stanford. I'm advised by Professor Monroe Kennedy. Oh, thanks. People who have amputations at or above the shoulder struggle to control prosthetic arms. And because the demand is so low, the hardware remains bad. So it's been shown that for prosthetic hands, for grasping, using vision and gaze tracking to estimate intent and augmented reality to communicate with the user can actually help a lot with manipulation. And we wanted to develop this for whole arms and for more complex tasks, but we couldn't find any good, affordable whole arm hardware. So we've made an immersive simulation platform for evaluating different intent estimation methods for prosthetic arms, and I'd love to chat more at my poster. Thank you.
Hello, I'm Samuel Clark in Jiajun Wu's lab here. While robotic perception is focused on visual signals, we can get complementary state information from audio signals For example, objects in everyday life make distinct sounds when manipulated, which are a product of intrinsic factors such as materials, as well as extrinsic factors such as contact conditions or posed relative to the listener. We took 50 everyday objects of different materials and made an automated rig to strike them with an impact hammer and move a gantry of microphones to 600 different positions around each object. And we processed our data and released it so it can be used for tuning and benchmarking new physics or learning-based simulation frameworks, or for other tasks such as interpolating object sound fields, like an acoustic super resolution. Thank you. See you at the poster.
Hello, I'm Janan. We are presenting FMB. So FMB is a benchmark for multi-stage functional manipulation, which means the manipulation sequence can actually depend on the relation between manipulation primitives. So in total, we have 9,000 human demonstrations, more than 70 objects, and all of them are 3D printed and totally reproducible. So here are two examples from the dataset. The left is single object manipulation, but still requires very dexterous manipulation skills. The right one is actually multiple object manipulation, but then they require to be put together in a very specific way, in an interlocking way, so which requires additional reasoning over the long horizon. So for more details, please check our posters.
Hi everyone, my name is Tia, and today I'm going to be sharing with you our research on efficient fruit counting using UAVs. So the idea is that we want to develop an autonomous fruit counting system that can optimize the visual coverage of all the fruit in an orchard by flying in between the tree rows at the canopy height. And this is enabled using our onboard obstacle avoidance planner. And with the AgriFly simulator we developed, we can quickly populate an agriculture scene in simulation and generate synthetic image outputs to help us evaluate our fruit counting algorithms. And on the bottom right, you can see the simulation results showing the advantage of flying at the canopy level compared to traditional methods such as flying over the canopy or using a ground vehicle. To find out more, please come to my poster. Thank you.
Hi, my name is Stephanie, and this is ReachBot. So ReachBot is a small robot that uses deployable booms instead of traditional robot arms for locomotion around Martian lava tubes. So at the end of each of ReachBot's booms, there's a microspine gripper, which uses these small spikes to adhere to lava rocks. But that contact interaction is stochastic. So we're trying to incorporate the stochastic grass model into uncertain aware motion planning. And in order to generate that grass model, we do a bunch of Monte Carlo simulations offline, and then we use a learned model to generate that grass. So if you want to learn more about this, come to the poster session, and also Mark Kokoski during the faculty talks will be talking later about some field testing that we did in the lava tubes.
Hi everyone, my name's Javier Yu. Today I'm talking about NerfBridge, which is an open source modular software package that's designed to interface ROS with Nerf Studio. The core idea behind NerfBridge is to be able to leverage sensor streams from a robot to train a Nerf in real time of the robot's environment. I'm really excited about applications of Nerf in robotics, and I was hoping that by designing this software package, I could save some PhD students some time. So if you're interested in any of those ideas, please come talk to me at the poster session. I'm really looking forward to questions. Thank you.
Hi, I'm Kedai. I'm a PhD student in the Stanford NAP Lab. So NASA is planning to deploy a network of satellites around the moon called the LunaNet to provide both communication and navigation services to support future lunar missions. And therefore, to achieve this mission, we are developing algorithms in the intersection of lunar navigation and communication. The first algorithm we are developing is the distributed positioning and timing framework using intersatellite range measurements. And we are using covariance intersection to achieve fully distributed estimation of the clock bias and the orbits. And also we are developing algorithms to optimize the intersatellite link scheduling, considering both communication, delay, and the navigation performance. To find out more, please come to my poster. Thank you.
Hi everyone, my name is Guanrong Tan. I've been working on designing an ankle exoskeleton that makes running easier. We do that by applying plantar flexion torques at the ankle with twisted string actuators. Oh, there you go. You can see the twisted string actuators in slow-mo in the second video. Essentially what happens is that as the user's foot strikes the ground, the motors kind of spin up the strings very quickly, causing them to twist and contract and apply a very large force on the heel lever. And it can apply up to 43 Newton meters of peak torque at the ankles. And in preliminary tests on one subject, we managed to reduce the metabolic cost of running by about 10.8%. And for outdoor tests at the self-selected speeds, we managed to reduce the cost of transport by 7.7%. Come check out my poster to learn more. Thanks.
Hello, my name is Jasmine Palmer from the Stanford Charm Lab, led by Elsa Nakamura. Haptic devices designed for interacting with virtual environments typically occupy the hands and fingers to apply mechanical stimuli. However, these devices can make creating more immersive virtual environments either difficult, impractical, or impossible for certain virtual, augmented, or mixed reality scenarios. Haptic relocation from the fingertips to elsewhere on the body has been shown in prior work to improve task performance, enjoyment, and user acceptance compared to scenarios with no haptic feedback. Here we present Hoxels, 3D printed soft pneumatic haptic voxel displays for simulating tactile interactions on the wrist or forearm in our goal to understand the best practices for haptic relocation from the fingertips to the wrist for virtual interactions. Please come to our poster to learn more. I'm looking forward to your questions.
Hi everyone, my name is Fadil from Stanford Intelligent Systems Lab, advised by Michael. In this work, we consider a problem of autonomous inspection in real-world environments where the robot needs to interact and examine different types of semantic objects. The main challenge in real-world inspections comes from the limitation of semantic understanding and limited knowledge of the environments. In this work, we propose a semantic-aware task planning frameworks to enable a reliable behaviors, semantic-aware behaviors by accounting for future semantic observation uncertainty. We demonstrate our solution in various inspection scenarios and shows that our approach enables a more efficient inspection behavior that are comparable to human-operated inspections. Happy to chat more in the poster session. Thank you.
Hello. My name is Charlotte. I'm a postdoc in Francesco Borelli's group at UC Berkeley, and I'm interested in controllers that allow autonomous systems to navigate unknown task environments safely and quickly. Let's consider car racing, for example. So even on their very first lap around a track they haven't seen before, professional race car drivers have no problem driving quickly and what I will call safely-ish, right? So inspired by this, I'm going to design a control approach that's based on how drivers learn to race, which I claim is by using these situational anchors or these features that relate different task environments. In this case, that might be the curvature of the racetrack. So we use stored trajectory data from previously solved tasks to learn these functions that map a local situational anchor to a low-level target set that we can implement in an MPC. And I too have a poster. So if you have any questions about how we implement this in a number of applications beyond racing, please stop by. Thank you.
Hello, 2 years ago, we introduced the smart suction cup featuring 4 internal chambers connected to the pressure sensors, enabling us to measure its internal airflow. Today, we are taking it a step further. So we've developed a model-based haptic search for the smart suction cup, adjusting its pose using this internal airflow we measured to find better grasp point. So to put it to the test, we've conducted beam picking experiment. From the result, we showed that our haptic search outperformed the vision-based algorithm that lacks this haptic feedback. So please come to my poster to see this little tiny but strong suction cup. Thank you.
Hi, I'm Xiang from UC Berkeley. So we are working on the contact-rich manipulation where the robot manipulates other objects using external contact. In order to do so, we need to have a feasible robot trajectory to set up the contact and a bunch of feasible gain parameters to establish a stable contact. However, it is difficult for us to learn something in the simulation and directly deploy in the real world because of the sim-to-real gap. So our idea of solving this problem is that the simulation can capture the geometry really well, but the main difficulty is the gain cannot be transferred. So we are using gain optimization module to enable the policy to apply to a diverse set of real-world tasks in the real world without any fine-tuning. Please keep by our poster for more details. Thank you.
Using no expert demonstrations, no reward engineering, and no manual language annotation, how can a robot scalably acquire language condition skills? We propose scaling up and distilling down, a framework for language-guided robot skill acquisition, and it has two parts. In the first part, we scale up language label robot data. By giving language models access to sampling-based planners, we combine the flexibility of common sense with the efficiency of model-based planning. In the second part, we distill down all successful experiences into a single closed-loop 6-degree of freedom policy. The result is a policy that does not rely on simulation state and performs long horizon, common sense, tool use, intuitive physics, articulated 6-degree of freedom manipulation, generalization, all geometry. You get the idea. To learn more, come find me, Hui, at the poster session. Thank you.
Hello, my name is Akshay, and I'm from the Hybrid Robotics group at Berkeley. So our work focuses on using control barrier functions for safety between convex sets. The motivation comes from the fact that over-approximating convex sets by spheres or ellipsoids can result in deadlock during control. But our method uses derivatives and Hessians, and they can be directly used in a CBF formulation. We find that for general convex sets, safety can be guaranteed at very little additional cost compared to spheres or ellipsoid. If you'd like to know more about our work, please come by my poster. Thank you.
Hi everyone, let me present to you M3L, a representational learning architecture based on mascot encoding that fuses both visual and tactile data into the same representation space, multimodal space, and uses these representations for reinforcement learning and manipulation. We train our architecture on various tasks and evaluate it on variations of the same tasks. What we found is that policies relying both on vision and touch generalize much better than those relying on vision alone. More interestingly, even training just a representation encoder with vision and touch also benefits policies that are then deployed at test time using vision alone. If you want to learn why this is exciting news, come talk to me at the poster session. Thank you.
Hi everyone, today I'll tell you about our work on sensory motor pre-training for robotics. The basic idea is to formulate robotic pre-training as a large sensory motor prediction problem. Specifically, given a sequence containing camera images, proprioceptive states, and actions, we mask out a subset of the sequence and task the robot to predict the missing content. So the intuition here is that if a robot is able to perform this prediction task, it has presumably acquired a fairly good model of the physical world that should enable it to act. After this pre-training stage, we fine-tune this model on some sort of task-specific behavior data, and we show that our approach can enable transfer across tasks, labs, and even different robots. Thank you, and please come to our poster.
Hi, I'm Lawrence. I'm here to talk about our recent work on manipulating deformable bags. Bags are ubiquitous in our daily life. They are challenging both for manipulation and perception. In this work, we study the task of bagging, opening a crumpled bag and inserting objects. Our key insight is that while it is very challenging for the robot to grasp a single layer of the bag, it can use interactive perception to help it adjust its grasp. Surprisingly, we found this strategy to be very effective across a variety of bags, significantly outperforming a prior algorithm. Additionally, we also find this to be very effective for singulating layers of fabrics and garments. Please stop by our poster to find out more. Thank you.
Hi everyone, I'm Wingsum. I work with Professor Sean Fulmer. Our group makes a lot of these shape-changing displays for things like haptic interaction, but these shape displays are often composed of a bunch of rigid bodies, which makes it really challenging to create smooth, curved surfaces. So to try and address that, we made this curved line display, which is based around the bending of a flexible rod. My collaborator, Sophia, modeled this system using the discrete elastic rods formulation, and using that model, we were able to make these these actuation instructions that take into account the system multi-stability to create a really wide variety of shapes. So as you figured out, I also have a poster, so please come talk to us.
Hi all, I'm Jerome Novak. You heard Sebastian Thrun say that it's difficult to deploy hardware at scale. That's one of the things we try to do at Prakash Lab to automatically diagnose malaria in the field. And what if, as a roboticist, you had to do some of this without access to electronics or electricity? Well, today I'm presenting Inkwell, a small open source device that automates whole blood sample preparation for malaria microscopy. It turns a single drop of blood into 8 million red blood cells neatly arranged in a plane, as you can see in the video. If you'd like to try to guess how it works or talk about injection molding to scale up our manufacturing, I'll be at the very far end of the poster session. Thank you very much.
Hi everyone, I'm Carlos Montenegro. In your work, we learn the Lyapunov function from data by enforcing the Lyapunov conditions to guarantee asymptotic stability in finally many sample points, building an epsilon net over the entire state space. And then using continuity properties on this epsilon net, we can guarantee a practical version of asymptotic stability. And then leveraging all this data we have and the learning model we got, we can also learn an upper bound on the cost associated to solutions to a dynamical system without neither computing solutions nor the cost itself. I'll be happy to take any questions in the poster session. Thank you.
Okay, thank you very much to the students. I know that it's very stressful to get through on time, but I appreciate the compromise we have. So now we get to break for some coffee and snacks, hopefully. I encourage everyone to chat to the sponsors, chat to the students at the poster session as well. And then we'll start back on time, 3:30, right back here.